Hello everyone, welcome to Physics Rocks It's True. Tonight we are going to look at work done and energy transferred. Kind of a mathematical one, this one, so let's get started. Okay, here we are with an energy transfer diagram very similar to the one we had last time, where we have some electrical energy going in to an electric motor and outcoming is some kinetic energy and some heat and sound. So the first thing to say about this topic is that none of the laws of energy are broken at any stage here. So total energy in is equal to total energy out. Okay, energy cannot be created or destroyed. It can only be changed from one form into another. So I've got 2,000 joules of electrical going in. I've got 1,500 joules of kinetic coming out, which means that down here I must have 500 joules of combined heat and sound because these are my only outputs. Okay, just like we had before. If you haven't seen the previous video, there should be a link in the description below. Alright, now what we want to talk about though is what is work done. Alright, now work is defined as equal to the energy transferred from one form to another. Okay, now normally we just don't bother with this from one form to another bit, we just go work is the energy transferred. Which isn't particularly interesting because the energy transferred here is 2,000 joules within and 2,000 joules come out, so 2,000 joules of work has been done. And that is absolutely true, but not what we're interested in tonight. What we're interested in here is the idea of useful work. And useful work, just like above, is actually the useful energy transferred from one form to another, but we'll leave that out. So in this case, the useful energy transferred is, yes, I put 2,000 joules in, but because I'm defining useful as being kinetic energy out of my electric motor has only done 1,500 joules of useful work. Some 500 joules of wasted work, 1,500 joules of useful work. And this equation here is one of the most forgotten about equations in all of GCSE physics. And the reason for that is that we're about to introduce you to the equation for useful work, which tends to be when people go and revise, they just revise the equations and don't bother revising the concepts behind them. This is very, very useful. Okay, useful work is the useful energy transfer. All right, but it has another form as well. Okay, and the other form it has is that the work done, and when we talk about work done, we tend to be talking about just the useful work done, is equal to the force multiplied by the distance moved. Now GCSE, that's fine. Technically it's in the direction of the force. Alright, so if you're pulling something diagonally, you're actually doing slightly less work than if you were pulling it in a straight line. But at this stage, we're fine with just work done is force times distance. Now notice I'm not using W here or anything like that, because W is weight, and we've been looking at that in a couple of our equations, and weight appears again in these ones. So we'll make W dot D be work done. Right, so that means that work done is equal to force times distance. Now, important stuff. First of all, work done is energy transferred. Therefore, it's a type of energy, or therefore it's a measurement of energy, and as such, it has to be measured in joules. No choice here, no calories, no weirdness going on here. This has to be measured in joules. Forces, by definition, are measured in newtons. And because we have joules and newtons here, and we have to use those units, then we are absolutely stuck with a distance measurement of meters. That's critical. There's no playing around with your unit here. It's not like pressure or moments where you can play around with the units and you can just provide you're consistent. It's okay. It's not okay to use anything other than meters here. Okay, and this is a common target point for the very famous sneaky examiner that will give you distances in centimeters. Right, for those of you who are, let's say, mathematically phobic, the little triangle for maths that goes with this looks like this, that work done sits at the top, forces at the bottom, and distance across here. Okay, and how we use this, for those of you who haven't been used to playing with triangles, we cover up what we want, and then what's left is the equation. So if I want force, it's work done over distance. If If I want work done, it's force times distance because they're beside each other. And if I want distance, it's work done over force. I'd prefer you to learn the equation and how to manipulate it. But if you're properly mathophobic, then this will do. All right. So how does this get used? What do we do with this? Well, let's have a little example. Okay, so let's take our electric motor. Okay, so this is our little motor, and let's put some energy into it. Okay, so it's going to be electrical, so we're going to put in some electrical energy. Let's say we put in 500 joules of electrical energy, and coming out of it, we're going to have, let's call it 300 joules of useful energy and 200 joules of wasted energy. Now, I know that the 300 joules is the useful one because of the way I've drawn my diagram, that useful energy progresses to the right, whereas wasted energy drops out the bottom. Okay, and let's say that my motor moves an object 5 meters. All right, what is the force provided by the motor? All right, so the first thing we want to do here is go, right, which one do we use? We've got 3 numbers here, but it's usefully moved the thing 5 meters. We're assuming that the motor is actually designed to move stuff, so its movement is 5 meters. So we're going to look at, because this is useful work done, we're going to look at this 300 joules here. So let's list what we know. We know that we've done 300 joules of useful work. We know that our distance traveled is 5 meters, and we're being asked to find our force. Alright, all the units are lined up nicely, so we go work done equals force times distance. 300 equals force, which we don't know, so that stays as F, multiplied by 5. Now we divide both sides by 5, because we don't want F times 5, we just want F, and that gets us that 60 equals F. So my final answer, F is equal to 60, and our unit is newtons because we have no choice in the matter. So usefully it's provided 60 newtons of force for that entire time. Now in reality it probably hasn't, it's probably varied left, right and centre, but remember we are modelling this thing as being kind of perfect, or not a perfect motor, but a consistent motor. Alright, and there's nothing more to it than that if you've been told what energies are being used. Okay, so look out for the catchwords here, that when you're talking about energy and force and distance in the same thing, then you're talking about work done. And that little semantic difference, that little difference in language is important. That this here is work done, but if you want to make it a little bit more difficult for you, because I've set slightly too easy an exam paper and I want to up the difficulty level, I will just talk about energy. Okay, and it doesn't matter what type of energy. I might say a motor usefully produces 300 joules of potential energy. Or I might say a motor usefully produces 300 joules of kinetic energy. Or I might say a motor usefully produces 200 joules of sound, because I like the sound of a motor as I go to sleep. Doesn't matter. As soon as you have useful and energy in a sentence together, you've got work. Alright, now, other way to make this slightly more difficult for yourself, or on you, is to try and work against gravity. Right, so let's take ourselves a little block here, and let's say it's a 10 kilogram block. And what we want to do is we want to lift this 10 kilogram block vertically upwards, and we want to lift it a distance of 4 meters. Right, what's the work done in lifting that block? The problem here is that we have a distance equal to 4, we have a mass equal to 10, we're being asked what's the work done, and we don't have an equation because we need a force. And we don't know how much we've lifted this with. Like, we could be an absolute beast and be lifting it with thousands of newtons, or we could be a little bit feeble and be lifting it with a lot less. How do we account for the different strengths of people in this question? The answer is, we don't. The earth does not care how big a beast you are when it comes to work anyway, and how much useful work you do. There is a concept called power, which will be our next video, that does take into account how powerful, how quickly you can do this work and how fast you can make it travel. But in reality, all we're interested in is moving this thing from here to here. And the minimum force that you require to do that is that you need to lift this with a force equal to its weight. Okay, so downwards on this object is we have weight equals mass times gravity. Weight is equal to 10 times 10, which is 100 newtons. So we know we've got 100 newtons downwards. So the minimum force that we need to provide here is 100 newtons upwards. We can provide more if we like, but that's not the point. We need to provide a minimum of 100 newtons. And physics doesn't care if you provide more, because the end result is that this thing ends up 4 meters up in the air. And the energy that's stored as gravitational energy is simply 100 newtons times 4, the work done putting it there. So the force that we need is 100. And again, we just crack in the same equation. W work done equals force times distance. Work done equals 100 newtons. Oh, don't need the M. Times 4. So work done is equal to 400 joules. And it's as simple as that, really. Just make sure you're nice and consistent with your units. Apply the formula. Look out for little newtony things all over the place, and you'll be absolutely fine. In the description below, you'll find a link to tonight's worksheet. Go now, click that, download it, and have a crack at the 4 questions there. They're not too difficult, take you about 5 or 10 minutes, and then come back and see me in a few seconds' time, and we'll go over the answers. See you soon. Okay everyone, welcome back. So let's get cracking to our question sheet. Okay, so question 1, 2 marks available here. What is the useful work done by this lift? And explain your answer. Now we've got an explain your answer section here, so the work done by the lift is probably worth 1 mark, explain your answer is worth another 1. Think about that during the course of your exam, because if the work done is only worth 1 mark, it's probably straightforward. Okay, so what is the useful work done? Again, we have to have useful work done. So useful work equals useful energy transferred. And the useful energy transferred here in a lift is, it goes from kinetic energy to gravitational potential energy. So the useful work is equal to 6,000 joules. Easy peasy, that's your first mark. Second mark, a little bit more tricky. Explain your answer, because you can go with 2 things here. First one you go with is the gravitational potential energy is horizontal in the diagram, and so is defined as useful. Okay, that's how you knew which one to use, because it was coming out across here. Or alternatively, it's a lift. Lifts raise things, and so GPE is useful. Lifts don't heat things on purpose. You don't think, I'm a little bit chilly, I'm going to go and put the lift on and move it up and down, up and down, up and down. Right, so either one of those is perfectly fine. You can do the simple from the diagram, by definition this is useful, or you can talk about the nature of the machine itself and how you would define its useful attributes. Question 2. A block is dragged with a force of 70 newtons for 20 meters. What is the useful work done on the block? Okay, so this is your straightforward, you've got things in a question, let's put them together. So first number we have here is 70 newtons. So F is 70. We have a distance of 20 meters. And I always put the meters in just to remind myself that we're okay for our unit. So that's there. And then what is the useful work done on the block? So we're looking to find what is the work done. So we go to work done. Alright, so work done equals force times distance. Work done equals 70 times 20. Work done equals 1400 joules. Okay. And this is a formula working answer unit 1 that we've seen before. So 1 mark for the formula, 1 mark for the correct substitution, 1 mark for the correct answer in unit. 3 marks. Question 3. A weightlifter raises a mass of 100 kilograms to a height of 2.1 meters. How much work have they done? It's a quick diagram. We've got our mass here, 100 kilograms. Get in the habit of writing masses inside objects. That helps you not confuse them with forces. How much work have they done? Now we got 5 marks here. Now that should be your first alarm bell. This is not a straightforward, get a work done 100 times 2.1, I'm out. Okay, so the first thing we're going to have to do is we're going to have to work out some forces. So first thing we have to do is work out the weight acting on this thing. And we use the weight equation, that W equals mg. Weight is mass times the force of gravity. So the weight equals 100 times 10 on planet Earth, because the force of gravity on planet Earth is 10 newtons per kilogram, equals 1,000 newtons. So we've got 1,000 newtons acting downwards in this, so that means we're going to have to provide an upward force of 1,000 newtons as well. So we have 1,000 newtons upwards. Alright, so now we've got our force. That gets you 2 marks to that point, 1 mark for W equals mg, 1 mark for the 1,000. So we've got work done now is unknown. That's what we're trying to do. The force is equal to 1,000 and the distance is equal to 2.1. And again, just like before then, we do work done equals force times distance moved, so F times D. Now for our work done is equal to 1,000 times 2.1. That means that my work done equals 2100 joules. Right, and again, marking system here, if we put a little tick, 1 mark for this, 1 mark for this, 1 mark for this, 1 mark for this, and 1 mark for this. And that gets you your 5 marks. Hope for that one, it's an easy one. Right, and then finally, an engine uses 80,000 joules of chemical energy in a certain time. 45,000 joules is converted to movement and the engine moves 1.5 kilometers. Now it's safe to assume that an engine causing movement that actually does move is exactly what we mean by useful. So we can start by how much useful work does the engine do. There's only 1 mark here. What is useful out of this? It's the 45,000. Press the right buttons would help. 45,000 joules of movement. So it's just 45,000 joules. Okay, B, what force on average is the engine producing? So again, what we have to do is we have to work our way through it. So our useful work done, our useful energy transferred is 45,000 joules. We want to find the force, so that's unknown. And we know that this thing travels a distance equal to 1.5 kilometers. And alarm bells go off in my head because I know the distance is not in meters here, so I need to convert that. When you see the word kilo, you just read the word thousand, so that's 1.5 thousand meters, which is 1,500 meters. Right, equation time, work done equals force times distance. So 45,000 equals F times 1500. So divide both sides by 1,500. So that gets us 30 equals F. So F equals 30 newtons. And that's all there is to it. Okay, if this video has been in any way helpful, please hit the like button. Consider subscribing if you've not already done so. Tell your friends, if you have any, I don't, about the channel. And all that remains for me to be said is physics rocks. It's true.